Okay, welcome back. Today we're starting a new unit on solutions. So remember at the beginning of the year, we said that matter was classified as elements, compounds, and mixtures. That was the first unit. Our second unit, we kind of took a detour and we did phase changes, and we talked about how particles and everything move and how the heat, the amount of energy affects their motion, and the more energy they have, the faster they move, and eventually they break the bonds and they change phase. And then we did Unit 3, which was a unit on elements, and then we did Unit 4 and 5, which were units on compounds. So we did elements, compounds, and guess what? Now here we are at mixtures, which is a solution. Okay, so we're going to talk specifically about solutions this time, not so much suspensions and the other mixtures, heterogeneous and homogeneous mixtures. Okay, so a solution, as we recall, is a mixture that appears the same throughout. That means it's mixed evenly. It's the same everywhere. Remember, it was the one where the particles are so completely dissolved that light would pass through it. And one of the things we didn't talk about earlier were the different parts of the solution. Okay, there's the solute, which is the stuff getting dissolved. So like if you dump sugar in water, the sugar is the solute, and the stuff that does the dissolving is called the solvent. So like if you go to Lowe's or Home Depot, wherever you go, they have different solvents, things that do dissolving. So we have mineral spirits here that helps dissolve paint, painter solvent that helps dissolve paint, brush cleaner, paint thinner, all this goof off stuff, all these things that dissolve stuff that, to remove stains or dissolve things. These are all different kinds of solvents. Water is also like the most common solvent, but there are other ones like these. Okay. A solution can be solid, like two metals that are melted together, and then so in order to make a solid solution that's even, you got to melt the substances first, mix them up, and then they re-solidify. Solutions can be liquids, okay, where we either dissolve a solid in it or mix two liquids. So like salt water is a solution that's a liquid. We dissolve salt into it. Okay. It can be a gas, like the air in the room is a solution, and it's a mixture of gases. You know that in the air there's at least some oxygen because you're breathing oxygen and you're alive. There's some carbon dioxide because you're exhaling the carbon dioxide because of respiration. And then the air is mostly nitrogen. So we know that there's at least three gases in the air. An alloy is a solution of metals. So like 18 karat gold is an alloy. It's a mixture of different metals, mostly gold. And we said earlier, gold is really soft, so it's too soft to make jewelry out of. So they mix usually something like zinc or copper into it to make it a little harder so that it's practical to use for jewelry. Okay. Now, how dissolving of ionic compounds happens. Remember, water is polar. It has a positive end and a negative end. Anything with poles has a positive end and a negative end. Okay. Water surrounds solute particles with the negative ends of the water attracted to the positive solute ends, and the water pulls the solute into solution. Okay. The combined particles move away and are replaced by fresh water spread out evenly. So here's this quick little video. I wanted you to see what happens during dissolving.
So how does salt dissolve in water? Well, let's start with a mixture of salt and water.
Now, you see how this is a salt particle. So the blue ones are the positive sodium, and the green ones are supposed to represent the negative chlorines. And you can see that the negative end of this water is attracted to this positive sodium ion.
The positive sides of water molecules surround the negative chloride ions.
And they become part of the solution.
The negative sides of water molecules surround the positive sodium.
Okay, so I paused this here and I added these positives and negatives. So the chlorine is a negative ion. Remember, we had a charge of -1. And the positive end of the water is the white hydrogen ends. And you can see how they're being attracted to this negative ion. And over here, this positive sodium is being surrounded by the negative ends of the water. Well, the water has enough negative to cancel the positive charge of the sodium, so it doesn't need the chlorine really anymore. And the same thing happens with the positive ends of the water. So the positives and negatives are attracted, but the chlorine now is attracted to enough of the water molecules and the sodium as well that they no longer are attracted to each other. And one of the properties we said of ionic compounds is they break into ions when dissolved. And this is why, because the water is polar.
Sodium ions.
And they become part of the solution.
The surface of the salt is constantly bombarded by water molecules, which dislodge ions.
This is called dissolving.
As time passes, the mixture of salt and water changes.
It becomes a solution with the salt dissolved in the water. After a while, the salt ions will be evenly distributed in the water because of the action of the molecules.
And this process is known as diffusion.
Science rules.
Diffusion happens spontaneously, without the addition of any more energy than what's already in the system. But how can we speed up the process?
By stirring, I can make the water molecules move faster.
This means they collide more often with the salt crystals.
Which speeds up the rates of dissolving and diffusion.
The molecules in hot water are already moving faster because of the added energy from heating. If I add salt to hot water, it dissolves more quickly.
If I stir the hot water, the salt dissolves even faster.
That gives us our fastest rate of dissolving and diffusion. So most particles dissolve and diffuse through a solution faster if you add hot water.
And stir.
Okay, so that kind of leads us up to this part. What affects the rate of dissolving? Well, there's three things that speed up the rate of dissolving. Okay, and most of them, you already know this. Okay, like they just showed us. Stirring speeds up the dissolving by bringing more fresh solvent into contact with the solute. Crystal size. If you mash the stuff up into a fine powder, it's going to dissolve faster than if it's in big chunks. So dissolving occurs at the surface. So like when they showed us that salt molecule, that doesn't happen in the center of the particle. It happens at the edges. So smaller pieces mean more solvent could hit the particle because more of it's exposed, so it'll dissolve faster. So sometimes if you go to a restaurant, they'll have it's like this brown sugar like this, and it's in big chunks, or they have more powdery sugar. You know, if you've ever used this stuff, it takes forever to dissolve, like you get iced tea or something. You pour this in there, and you stir and you stir and you stir, and because water is cold, and that's the other thing we're going to talk about. Okay, you have these big chunks in cold water. It takes forever for this stuff to dissolve. Whereas this kind of sugar, where the crystal size is smaller, the water can get to all sides of the sugar particles faster, and it speeds it up. Okay? And you know that dissolving things in high temperature speeds up the dissolving. So if you want to get sugar to dissolve in water, it dissolves much faster in warm water than it does in cold water. Okay? Higher the temperature, the more the particles move. The more they move, the faster they break apart and dissolve. Now, when we talk about a gas, this is all for a solid and a liquid. Okay? So like dissolving sugar or salt, things in liquids. But we dissolve gases in liquids as well. So like, you know that there's oxygen is dissolved in water in a pond so that the fish can breathe. Okay? If there wasn't any dissolved oxygen in there, they would suffocate. So that's why, like in an aquarium, it bubbles, and it bubbles to mix the oxygen into the aquarium water so that the fish can keep breathing. People also mix gases into liquids so that they make carbonated beverages. So the carbon dioxide is mixed into the liquid, and it stays there to give the soda its bubbles. Now, mixing a gas into a liquid is exactly the opposite conditions of mixing a solid into a liquid. So you get the gas particles, which already have a lot of energy. You want to get them to slow down and not have as much energy so that they stay in the liquid. So you want to decrease the temperature of the solvent. And think, like if you have a really hot soda, like, on a summer day, and you open it up and it hasn't been refrigerated, the gas wants to become undissolved almost immediately and it explodes. You need to keep it at high pressure. That's why you keep the tap on a liter bottle of Coke. You keep the pressure on in there so that the soda stays dissolved. And then you don't want to stir it and shake it. Again, if you think about what happens when you stir or shake a Coke or a soda, it becomes undissolved.
In the middle here, I've measured 1 teaspoon of the granulated sugar, and then we have 1 sugar cube, which equals 1 teaspoon of sugar. And we're going to add them to the water and see which one dissolves first. Okay, on your left, we're going to add the 1 teaspoon of granulated sugar, and on the right, we're going to add the sugar cube. And I'm going to try to do it at the exact same time. I'm not going to stir or agitate either cup, and we're just going to see which one dissolves first. So here we go. So at this point in the experiment, neither glass has completely dissolved the sugar, but I think it's pretty evident which glass has more of the sugar dissolved and which glass or which circumstance or which experiment dissolved the sugar faster. Okay? Thanks for watching. Bye.
Now, this one is going to show us the difference in temperature. So we got hot water on the left and cold water on the right. They put a sugar cube in each. Okay. And we would expect that the hot one should dissolve faster than the cold one. You can see that the hot one is beginning to break apart. It's losing its shape. Particles are starting to fall off. This one is still pretty much looking like a sugar cube. Okay. This one, the heat is really starting to affect it as particles vibrate faster and faster. The cube is starting to break apart. This sugar cube's really going to pieces now as it sits here in this hot water. Okay, so we said particle size we saw in the first one. They were both in cold water, and one was a sugar cube and one was the granulated sugar. And smaller particles dissolve faster. We said the other thing that affects dissolving is temperature. You can see that in the hot water, the sugar cube in the hot water is dissolving a lot faster than it is in the cold water. And then the third condition we said, which should be pretty obvious, is stirring. And then this little clip is going to show us stirring.
So now we're going to see the effect of agitation or stirring on the rate of solution formation. So to start out, I'm going to add 100 milliliters of water to each of our beakers. And then we're going to place about 1 gram of salt in each at the same time. So I'm going to stir one and not stir the other. So at this point, all of the salt in the stir beaker has been dissolved.
Okay, and then there's gases, the rate of dissolving of gases. So I want you to take a quick look at this video.
Hi everybody. In this demonstration we're going to be looking at factors that can change the solubility of a gas in a liquid. The gas that we're using is carbon dioxide, the liquid is water, so we're using a bottle of seltzer water, which is bottled at very high pressure, pushing carbon dioxide molecules into solution in the water. So what we're going to be using are 3 different bottles of seltzer water. I've got one that's been sitting out at room temperature, another one which is in a warm water bath, so we're heating that seltzer water up. And then finally, the third one here has been sitting in a large beaker with ice water in it. So we've got seltzer water which is really cold, seltzer water at room temperature, and seltzer water which has been heated up to quite a warm temperature. So we're going to take a look at what happens when we open these bottles. So this is the seltzer water which has been left out at room temperature. So I'm going to go ahead and open this up and let's take a look, see what happens as I open the cap here. Okay, so we can see that it fizzed up quite a bit, and what's happening right now is the carbon dioxide molecules which were dissolved in the water are coming out of solution. So that's producing the fizz, the bubbles that we see. And I kind of made a mess here, so I need to clean up before we look at what happens to the bottle that was in the cold water versus the one that was in the hot water too. Alright, next we're going to take a look at what happens when we open the seltzer water which was placed into the ice water bath. And just so we can see this a little bit more clearly, I'll just wipe off some of the condensation that's on the bottle before I open it. So we'll try to do that quickly.
So remember,
Just to remove some of that
this
condensation
is the
so you can see
opposite
what
of
happens
mixing
here.
a
Okay, so here we go. We're
solid
now
and liquid.
opening the seltzer
colder-
water bottle that was
colder it
placed
is,
into
better
the ice
gas
water
should
bath.
stay mixed.
We can see that the carbon dioxide, which was dissolved in the water, is coming out of solution.
Nowhere
I want to
near
think
as
about
fast as the
comparing
warm
how
water.
rapidly is the carbon dioxide coming out of the water when it's cold versus how quickly did it come out of the water when the water was at room temperature.
When it was at room temperature, it didn't want to stay dissolved as well.
Not as
So
big of a mess
the
to clean up
colder
this time.
is better. Now, the hot one.
For the last part of this demonstration, let's
the
take a look
gas
at
in
what
the
happens
liquid.
when we open the seltzer water that was placed into the hot water bath. I think I might get messy on this one. Let's see what happens.
So heat is bad for mixing a gas in a liquid.
Okay, my custodial staff is not
Opposite
going to be
of a
happy
salt
with
in a
me,
liquid.
but hopefully after seeing this demonstration you get a better feel for how the temperature of water can change the solubility of a gas in the water. Thanks for watching, everybody.
Okay. And then I want you to go ahead and answer these questions on your own, and we'll pick up here next time. I hope you're having a great day. Thanks for watching.